we start with a very important part, rotational kinetic energy. We have already studied about the translational kinetic energy when we have studied the chapter of work, power energy. In energy, we have studied what is known as kinetic energy. Kinetic energy is the energy possessed by a body by virtue of its motion, or rather velocity. Half mv square is the translational kinetic energy. Here we are going to study the rotational kinetic energy, and after that we will study some examples in which there will be both translational as well as rotational kinetic energy. So if we consider a body, now suppose three axes if we take this is x, this is y, this is z. Now if we take a body like this, we take a mass m here. The mass m here, the mass is moving with the velocity v in this direction, and the distance of this mass from the origin is r. So we have considered a body rotating about an axis. Now this axis is the axis z, because the body is rotating with respect to the axis x. Now we have chosen a particle of mass. How much mass? Mass of small m with a velocity of v and direction distance is smaller. Now the kinetic energy of the particle, what is the kinetic energy of the particle? We know the formula from translation, that is half mv square. Now if we replace v is equal to r omega, omega is the angular velocity and r is the radius or the direction distance, now is equal to half of m into v square means r omega square, that is half m r square omega square, that is mr square. We have already studied about this term mr square. We know it, that is I, or the rotational inertia, the moment of rotational inertia or moment of inertia. So the kinetic energy for rotational motion, so rotational kinetic energy, if you can write it like this, we get it to be half I omega square. Now any body like a ceiling fan, rotates about its axis continuously with the angular velocity of omega. So here for that case we have pure rotation, so the value of kinetic energy for that case is half I omega square. Now we are going to handle some cases in which there is both translational as well as rotational. So kinetic energy due to translation and rotation both. So k, we can write k of translation, trans, plus k of rotational. Now the formula goes as half mv square plus half I omega square. A vivid, clear example you can get from cricket, spin ball. Now when a bowler spins a ball, he throws the ball. So when he throws the ball towards the batsman, he gives a translational kinetic energy, and he also spins the ball with his fingers. Now when he gives a rotational motion on the ball, when his finger rotates on the ball starts to spin or rotate, and while moving forward in the direction of the batsman, the ball also is rotating. So if the ball is rotating, it has got a kinetic rotational energy or rotational kinetic energy. In that case, if we can write the example as spin bowling, the best example to describe a motion which is both related to translational as well as rotation is spin bowling. Now we start with rotational work. Now in linear motion or translational motion, we have studied about work. Work was force into displacement, F dot S. So if we can write the rotational analog of both force and displacement here, we can get the rotational work formula. So it was instead of force we have to write tau, rotational analog of rotation is tau, and linear displacement replaced by angular displacement. So the formula will be W is equal to tau dot theta. Tau means the torque and theta is the angular displacement. Now if you can try to explain it in this way, Again 3 axis body. There is a force acting on the body F. The body rotates from this position to this position. So the angle displaced by the body is delta theta. Angular displacement is equal to delta theta, and so the work done is will be equal to the force into displacement. Now the displacement here will be like this in a curved line. So F is equal to, we know S is equal to r theta. So the radius of the, or the length of the path from the origin to the point where the force is acting is smaller. So r delta theta, F into r delta theta. Now what is F into r? F into r means tau delta theta. So the magnitude of the work done in case of rotation is the value of tau multiplied by the angular displacement. For a variable torque, this is the case where torque is constant. Because remember, when the torque is constant, we can apply this formula, or vectorially we can write dot theta. Now for variable torque, the torque is changing, the applied torque is changing. So variable torque, we have to get the value of W, or the work done in rotational motion, is with the help of integration. So tau d theta from theta 1 to theta 2. So the angular displacement, the integration is done with respect to the angular displacement. So theta 1 to theta 2, the initial position was theta 1 and the final position is theta 2. So with this line, this angle was theta 1 and this angle is total angle is theta 2. So the displacement is theta 2 minus theta 1. Now power delivered by torque, power delivered by torque. So what is the power delivered by torque? It is, we all know delta W by delta T. We can write power as change in the work done with respect to time. So we can write this as tau delta theta by delta T. Now delta theta by delta T is delta omega, or omega. We can write it as tau omega. So P is tau omega. Now Newton's second law of motion for rotating body. For this, or to prove it, just a recollection of what we had done in the translational motion. That is, for Newton's second law of motion, the derived formula was F is equal to ma. So by the rotational analog part, we get, instead of F we have to write tau, instead of m we have to write a, and instead of a we are writing alpha. So tau is equal to I alpha. Now two relations we have already learned. Tau is equal to r cross f, and another one is L is equal to r cross p. That means one is the torque, another is the angular momentum. So just as we have done in the translational motion part for Newton's second law, that is rate of change of momentum, here we have to do the rate of change of angular momentum. So rate of change of angular momentum is dl by dt. So we write r cross p instead of L. This is a derivative u into v. So we can write here dr by dt into p plus derivative of p dp dt. Now, as this is a cross product, we have to take into account the position of these two terms. We cannot write here dp by dt cross r. It must be r cross dp dt. Now dr by dt means v cross p plus r cross, now rate of change of linear momentum. dp by dt means rate of change of linear momentum, that is force, again that is from the Newton's second law. Now if we take P as mv plus r cross f. Now what is the cross product of v cross v? The same. V cross v means similar vectors. Cross product means it comes to 0, because the angle between them is 0 and sine 0 means 0, plus r cross f. Now what is r cross f? From the first relation that we have written, that is r cross f is equal to tau. So you can write here r cross f means tau. So dl by dt, r cross f means tau. So this is the statement, or you can write tau is equal to dl by dt. So we can write rate of change of angular momentum is equal to the external torque. So rate of change of angular momentum is equal to external torque. So from the linear system, uh, this is a statement of Newton's second law for the rotational case. If external is equal to dp by dt, rate of change of linear momentum is equal to the implied force or the applied force. Now L is equal to I omega, if you write it vectorially. So that is L is equal to I omega. Now what is tau external? It was dl by dt. So ddt of I omega, dl by dt, instead of L we have written here I omega. I is a constant term, so it comes out of the derivative d omega by dt. Now what is d omega by dt? So tau external becomes I alpha. Tau external becomes I into alpha, where alpha is the angular acceleration. It is the angular acceleration. So after we have completed with the Newton's second law, let us move on to the angular impulse. Angular impulse. What was impulse in the translational part? It was a product of the force and the time. It was a product of the force and the time. Product of force and time gives the impulse. Or rather we can say it was the rate, it was the change in linear momentum. Either we say that it is a product of the force and the time, or change in linear momentum. Here, if we can again write it by the rotational analog type, instead of f we have to write tau, and t remains as t. So tau into t becomes the angular impulse. So here also we can write, this is the impulse, but we have to write it here angular impulse. For that we can write the statement in this fashion also. This was known as the change in linear momentum. So for this part we must write change in angular momentum. Change in angular momentum. If you consider a body hinged at one end, if we can apply a force F, suppose this is a door, it can be hinged at this end, or rather hinged here. We apply a force F. The direction or the distance from the hinge to the point of application of the force is R. So we can write tau is equal to Fr. This is F, this is R. So the torque is tau is equal to F into R. Now the product of torque tau with the duration of its exertion or the application, either exertion, you can tell exertion or application. So the product of the torque, product of this torque and this time delta t. Now what is delta t? Duration of its exertion is called angular impulse. So this is known as the angular impulse. Tau delta t, angular impulse. So again we know tau external is equal to dl by dt, as we have discussed previously. Rate of change of angular momentum is equal to the applied torque or external torque. So dl is equal to tau external dt, tau external and dt. So this is known as the angular impulse. So if we are given a problem in which we are asked to find out the angular impulse, we can do it in two ways. Either tau external into the time taken to get the change, or the change in angular momentum. Change in angular momentum. Now we start with the conservation of angular momentum. So far what we have studied, we have studied about two conservation laws, two very powerful conservation laws. One is the conservation of linear momentum and another is the conservation of energy. Here we are going to study another conservation law, or rather the third law, the conservation of angular momentum. Now what is that? Tau external dl by dt. We have learnt about this in the previous page. So tau external is equal to dl by dt. Now if no external torque acts on the system, the equation becomes dl by dt is equal to 0. So dl by dt is equal to 0 means L is a constant. Now after this I am going to write for an isolated system. This is not applicable for system which is not isolated. Only an isolated system where we can write if the torque external is 0, that means L is a constant. Now examples of conservation of angular momentum. So the heading goes as examples of conservation of angular momentum. The first one you can take as the planetary motion around the sun. Planetary motion around the sun. Now this is not a very easy thing, because in planetary motion the gravitational force, the force of attraction between the body masses are converted to centripetal force and always passes through the axis of rotation. This centripetal force always passes through the axis of rotation, so its moment of force is 0 as the axis passes through the axis of rotation, or the line passes through the axis of rotation. So its moment of the force is 0, and therefore the angular momentum of the orbiting planet remains constant. For a planet like this, the sun, the planet is rotating. If we take this as the sun, so let this point, if we take it to be with a velocity of v1, we take another point here, let the velocity of this not like this, v2 tangential. Now r2 is the length or the distance between the sun and the planet, r1 f. So f is the centripetal force. Now in this case m1 v1 r1 must be equal to m2 v2 r2, where v1 and v2 are the speeds of planet in two positions. So m1 v1 r1 is equal to m2 v2 r2. Now here m1 is equal to m2 because of the same planet, because the planet is the same planet is equal to m. So v1 r1 is equal to v2 r2. If we take another example, like a person sitting on a rotating table, he takes two dumbbells, two hands, one dumbbell here and the dumbbell here. Okay. So when he L is equal to I omega. Here also we can write I initial, omega initial is equal to I final, omega final. I f final is less than the initial, therefore omega f must be less than omega I. Now in this case, when the person he closes the distance between the two dumbbells onto his chest, then the rotation of the seat is there. But if he stresses his hands, that means increases the value of r, then the angular velocity of the chair decreases, it slows down. So taking the hands together near the chest will reduce the value of r, in turn increasing the value of angular speed. To reduce this, he has to stretch his hands onto both of his sides to increase the value of r, so that omega decreases on its own.